Good morning, Gear 4. How are you guys? So, today we're going to continue talking about magnetism, and we are going to talk about the definition of the word magnetic field. And we are also going to know the relation between the north and south pole of a magnet and the north and south pole of at the beginning, I would like to correct the homework that was due today with you. So it's really simple. You just have to specify whether those objects are magnetic or non-magnetic. So let's start together with the first object, which is the copper coin. And let me remind you of the statement that we said. It will remind us of the type of materials that could be magnetic. So it is IC nickel. I is for iron, C is for cobalt, and the word nickel, of course, and we added to them steel too. So we have four materials that are magnetic, which are iron, cobalt, nickel, and steel. So copper is not one of them, and that will make the copper a non-magnetic material. The next one is silver coin again. So the same, it's not one of the four main materials, so it's non-magnetic too. The pencil is mainly made of wood, so the pencil, of course, is a non-magnetic material. Drinks can. The can is mostly made of aluminum, and again, aluminum is not one of the four materials that we consider magnetic, so it's again non-magnetic. Now, someone asked me the paper clip. What is it made of? The paper clip is mainly made of iron, or steel. So this will make the paper clip magnetic. And the spoon, I told you to consider it a steel spoon, so this will make it magnetic too. As for the saucepan lid, we consider it glass, so glass, of course, is a non-magnetic material. So now we're going to start with our lesson. We want to know what does magnetic field mean. So magnetic field is mainly the area that surrounds the magnet. This area that surrounds the magnet, or the area that the magnet still has force over it or power over it, is called the magnetic field, which means that, for example, if this lines represent the magnetic field, so if I'm going to add or to put an iron nail in this spot, the spot that I kept the laser point at, it will not be attracted to the magnet because it's outside its magnetic field. It's outside its power. But if I got the iron nail closer to the magnet, and now the iron nail is or entered the magnetic field of this magnet, so this will make the iron nail get attracted or get stuck to the magnet. So this is called the magnetic field. It's the area around the magnet that still has magnetic force, or that the magnet still has power over it. So those lines, as you can see, represents the magnetic field. It always gets out of the north. The magnetic field always, or the magnetic force always gets out of the north pole and gets into the south pole, and so on. So it always gets out of the north pole and gets into the south pole from any direction. So if this is the direction, the north, the magnetic force will get out of it, which is the north pole. So it's going to make a complete circle and get in again in the south pole. So is this one. It will make a complete circle and get to the south pole again. Here, as you can see, it's getting out of the north pole to the south pole. So any magnet, the magnetic force in any magnet gets out. Its direction is from the north pole of the magnet to the south pole of the magnet. As you can see, the lines get really close to each other when they are closer to the two poles. So when they are closer to the two poles, you will find the lines are very close to each other. When they get away from the two poles, it's very obvious over here. When it gets away from the poles and starts to move towards or closer to the center, they start to get away from each other. So as you can see, at the two poles, the north pole and the south pole, you will find that the lines or the magnetic force is very strong, because the more the lines, the stronger the magnetic force. So you will find that the force or the magnetic force in the two poles, you will find the lines are very close to each other, as you can see. But when they get to the center, when they are passing by the center, you will notice that the lines are getting away from each other, and this means that it's really weak. The magnetic force is really weak at the center of the magnet, and really strong at the two poles. So the field lines are closer at the poles rather than the center. The closer the lines, the stronger the spot. So this will make the two poles the strongest among the whole magnet, while the center is the weakest. Now, how is the north and south poles of the magnets related to the north and south pole of Earth? Now let me tell you something. Earth is actually a very giant magnet. It's actually we consider it a very giant magnet. And the north and south pole of a magnet is actually, if you decided to hang a magnet by a thread in the air, you will find the magnet keeps orbiting, or keeps revolving, or keeps circling around until it stops in a specific point. When it stops at this specific point, you will find you can determine the direction of the north and south pole. The part that the magnet stops at, or the point that the magnet stops at, it is actually pointing at the north and the south of the Earth. Why? This is because the Earth is actually the metals inside it, which is the iron or the cobalt or the nickel, inside the Earth itself or under the ground, makes the Earth a giant magnet. But the problem is it's a little bit different, or a little bit tilted than the actual north and south pole of the Earth. So if this is the north and south pole, which we call it the geographical north and south pole of the Earth, the north and south pole of the magnet is a little bit tilted to the left. Okay, so the geographical north and south poles differ from the magnetic ones, but not a very big difference. It's just a slight difference, as you can see. So this is the North and South Pole, which is in a straight line, as you can see. The magnetic North and South Pole is a little bit tilted from the actual or the geographical North and South. Now, if I have a magnet, which is made, of course, of iron, cobalt, or nickel, or steel, and I'm not going to use it for a long time, and I want to store it or keep it working for a long time. The problem is that magnets, by time, if they are not kept in a specific way, by time the magnetic force, they start to lose their magnetic force. And after a specific amount of time, if there is a piece of iron which is a natural magnet, after a specific time it will start to lose this magnetic force, which will make it just a piece of iron, not a magnet anymore, because it will start to lose magnet. You can consider it, for example, if you have a steel spoon, for example, and you heat up this steel spoon or a steel rod, and you keep heating it and heating it and heating it, and then you will keep after that you will just remove it from the fire, and you will keep it at any table, just in the room temperature. After a while, if you touch the steel rod, you will find it cooling down, or you will find it getting cold. This is because the heat energy inside it is getting out of it to the surrounding area. The same happens with a magnet. A magnetic force inside the magnet, if it's left not kept in a specific way, the magnetic force will start to be lost in the surrounding area. So how can I keep a magnet working, or how I can protect it from being from losing its magnetic force? By something called a keeper. This piece of it's mainly made of a magnetic material, so it could be an iron, or a piece of nickel, or a cobalt, or steel. Any one of those four materials, we call it a keeper. And this keeper, we stick it to the magnet, and this way the magnetic force will never get lost, because it will keep moving around. The magnetic force will keep moving around from the magnet to the keeper, again to the magnet to the keeper. It's just moving around inside it. So this will not make the magnet lose any magnetic force in the surrounding it. So the keeper preserves the magnetic field, as I told you. Here's the keeper, and it just, the magnetic force starts to move around, or keeps moving around, and this will make it preserved inside the magnet. So how do you preserve a bar magnet, for example? Again, by using a keeper. You will get 2 bar magnets, and you have to put them in an opposite way, as you can see. So the north poles are opposite to each other, and the south poles are opposite to each other, and then you're going to stick both of them to 2 keepers at the bottom and at the top. And this is the direction of the magnetic field, and this is the point of the keeper, that it just keeps the magnetic field preserved, or stuck inside the. Now let's make the classwork that we could not do in the live session. Metals can be attractive. We have some observations. Magnets are usually made of the metals iron, steel, or cobalt, and I'm going to add to them nickel too. When a magnet is held near an object made of the metals iron or steel, the magnet pulls the object toward itself. Now we have a science activity. Mika said that magnets attract all metals. Raquel said that magnets attract some metals, but not all. They did an experiment to find out who was right. Color in each of the metal items that you think will be attracted to the magnet. So I want you guys to color them. I think we all know that the things that will be attracted. Now let's think about it. I will give you a second to think about it. So yes, the cast iron saucepan is one of the things that will be attracted because it's made of iron. Steel spoon, of course, is going to be attracted to the magnet. So this will make who right. Who was right? Is it Mika who said that all metals get attracted to the magnets, or is it Raquel who said that some metals only get attracted to the magnets? Yes, you were right. It's Raquel, which said that only some of the metals get attracted to the magnet. Now worksheet number 7, magnet magic. Background knowledge. A magnet is a type of material that pulls on some metal objects. The magnet is said to attract the object. Magnets attract the metals iron, cobalt, nickel, and steel, but they do not attract other metals. Magnets can attract or repel, push away another magnet. The force of a magnet can be felt from a distance. For example, an iron nail placed near a magnet will move toward the magnet. It looks like magic, but it is just the force of magnetism. Science activity. Draw a line from the magnet to each of the metal objects that will most likely attract. So this is a horseshoe magnet, and we have here a bunch of objects made of metal. And again, we will get back to the previous worksheet where we said that not all metals get attracted to magnets, only specific types, and I will remind you with the statement I see nickel and steel. Okay, so iron, cobalt, nickel, and steel. So that means that the gold ring will not be attracted, of course. The copper nail is the same. Aluminum kitchen foil, no. Brass screw, and again I will remind you that brass is a mix of copper and zinc, and both of them are non-magnetic. Now we have a steel paper clip, yeah. A steel pen too, very good. So only those two are the objects that will be attracted to the horseshoe magnet. This is it for today, guys. So this is your homework, pages 81 and 82, and it's due on Monday. I'm going to give you the pages number on Google Classroom, and I want the homework be delivered on Monday. So it's very easy. You just have some multiple choice in both pages, as you can see. They are all related to what we just learned in the previous sessions. Inshallah, next week, guys, we will be talking about the first thing that we're going to talk about next week is how is electricity and magnetism are related to each other, and this is a very tricky thing, or it's a very nice part of the lesson. You're going to enjoy it, inshallah. Until then, guys, I hope you're all great. It was very, very lovely talking to you yesterday, and I'm looking forward to do it again. Until then, I miss you all and see you soon. Bye bye.